we have Landon and Hazel talking about the thermocouple time constant.
Hello, my name is Landon Hazel. I'm also going to be talking about the thermocouple time constant experiment. My experiment was different from the previous ones that we've heard about because mine was put into a ice bath rather than a boiling beaker of water. So this is just an outline of the presentation. I'm going to go over the experiment and just give you a synopsis of the theory, talk about the apparatus and procedure, and then I'm going to present my raw data. And I've got my raw data separated into insertion and removal, and then I'll talk about the data analysis and discussion. So a thermocouple, it's I've got a picture of it right here. You're basically just going to be a measurement device to measure temperature that plugs into a data acquisition unit. The thermocouple transient response can usually be estimated if heat transfer coefficient is known, but usually it's not, so therefore it must be taken experimentally. So the overview of this experiment, we wanted to record the transient response of the 1/8" type K thermocouple probe and on insertion and removal from the ice bath. And then we wanted to, from that, figure out the time constant of the experiment. So we use the lump capacitance method, which the lump capacitance method basically, the biggest assumption is that the temperature is going to be, it's going to be distributed equally throughout the entire whatever fluid that the thermocouple is in. So the rate at which heat is convected to or from the system and the rate of change of the thermal energy within the system is balanced. And if we set the initial conditions of time and temperature to 0, will result in this equation. And it can be rearranged using this as our time constant. As discussed earlier, as far as this experiment, the only thing that's going to change is the heat coefficient. So as far as the apparatus, we have a 500 milliliter flask full, half full with ice water, and then we've got our thermocouple, and we've got our paper towels to wipe off the thermocouple, which is very important, and then the computer, which is connected to the PDAC, which is under the desk, which you can't see, and that's our ice. This is the procedure. We've already talked about it. Basically, we're going to open the computer up, stick the thermometer or the thermocouple into the beaker in the ice bath, and then take it out, and we're going to record all the temperatures during that process. So as far as the raw data, here is the insertion. As you can tell, it was about 17 seconds of time, but that I've got recorded, but it actually stopped changing temperatures at about 6 seconds. And then for the removal, it actually took 600, so about 10 minutes, and it was a much longer transition time. As far as the normalized temperature versus time, we've got, it looks very similar to the original. It's just with normalized with 1 to 0 rather than from the ambient temperature of 21 to 0 degrees. For the log of the normalized temperature, I've got it, and I set the the y-intercept as 0 to make sure that there was no plus or minus right here. And it ended up with, for the insertion, it was 2.1823 was the time constant. The removal, like I said, there was a much longer time period, so if there was any fluctuation in the temperature, it's not as evident in this one. And then but it is evident right here because you can tell that we've got one really outlier, but everything else is about the same. And it's a much higher, at 123 was the time constant. Like I've said, the thermal time constant for insertion was 2.1823 and removal was 123.04. The heat transfer rate is much higher in water than air. I mean, if you think about it, if you walk outside into, let's say 32 degrees